Welcome to 1600X, an introduction to aerospace engineering. We're going to spend the next 2 months looking at astronautics and human spaceflight. But before I tell you about the content of the course, I think I should introduce myself because you're going to be seeing a lot of me over the next couple of months. My name is Jeff Hoffman. I'm a professor in the Department of Aeronautics and Astronautics at the Massachusetts Institute of Technology in Cambridge, Massachusetts. Prior to coming to MIT, I spent 19 years as a NASA astronaut.
Mission Specialist Jeff Hoffman.
Making 5 missions on the Space Shuttle.
And we have liftoff of the Space Shuttle Endeavour.
And 4 spacewalks.
Hello, Jeff.
Including 3 during the critical 1993 rescue mission, where we installed corrective optics into the Hubble Space Telescope, allowing it to focus clearly. I actually started my professional career as a scientist, studying high-energy astrophysics, that is, X-rays and gamma rays coming from celestial objects. This radiation doesn't penetrate the Earth's atmosphere, so we had to do our research by sending telescopes up into space using balloons, sounding rockets, and satellites. So space has always been an important part of my professional career. Even as a young child, I was fascinated by space. I grew up during the early days of the space age, and I remember the launch of the first Sputnik and the flights of the first astronauts, Yuri Gagarin, Alan Shepard, John Glenn. I always thought to myself, this is really exciting, something that maybe I'd like to do, riding in a rocket someday, but all the early astronauts were military test pilots, and that wasn't something that interested me. So I guess my interest in space led me into a career as a research astrophysicist. I was working at MIT in the Center for Space Research in the mid-1970s when NASA was preparing for the operation of what was then the brand new Space Shuttle. The shuttle had a crew of 7 people, and only 2 needed to be pilots. So NASA said that they were looking not only for pilots, but for scientists, engineers, and medical doctors, and I thought, this is my chance. I took advantage of that, applied, and was lucky enough to get selected, and of course that changed my life. After a very exciting and productive career as an astronaut, I came back to MIT, this time as an aerospace engineer. 3, 2, 1, drop. I love teaching. Oh, it was good until it collapsed. And I love getting my students involved. Very pretty. I have no idea how it's going to fly. One of the courses I teach at MIT is the Introduction to Aerospace Engineering for first-year undergraduates. Now, I spend 4 months teaching the live course, and in the 2 months we have available for this online course, I can't cover all the material that we cover in the live course. So we're going to concentrate on astronautics, and in particular in human spaceflight, in which, of course, I have a lot of personal experience.
Okay, Jeff, outstanding.
So let's take a look at what we're going to learn in 1600X. Welcome to 1600X, an introduction to aerospace. This is a course about aerospace engineering, but I want to start by taking a look at engineering in general. Human beings have actually been doing engineering ever since cavemen first learned how to make tools out of stone, and there have been some incredible engineering accomplishments throughout the course of human history, from the Egyptian pyramids to Roman aqueducts to the Great Wall of China to Gothic cathedrals. There are some basic principles which apply to all types of engineering. Let's take a quick look at some of the things that engineers have to be conscious of when they're doing their work. First of all, engineers rely on what they understand about the natural world around them, and they use scientific discoveries as the basis for the constructions, the designs, the things that they're going to actually make, so that we can actually harness the aspects of the physical world around us to make useful objects. And usefulness is another critical aspect of engineering, because we don't do engineering in a vacuum. And I'm not talking about aerospace engineering here, I'm talking about engineering in general. Engineers are a part of society, and one of the first things that you have to do is to identify a need for something that doesn't exist, or something that is already in existence but has some problems which you can maybe improve. So we have to be conscious as engineers of our role in society and look at societal needs as a driving force for what we do in engineering. And once we identify a need, then we have to devise the processes, the equipment, basically the systems that we use to solve those problems. And I want to concentrate on communication as a part of engineering. Many people think of engineers as spending all their time just sitting at their desk working with a computer, but being able to communicate is critically important. You can have great ideas, great designs, but if you can't communicate those ideas to other people, then you're really not going to have success in being able to realize your concepts. So we emphasize communication in our engineering education here at MIT, all different types of communication: oral, written, stand-up presentations, PowerPoint, making videos. Communicating ideas is absolutely critical for your success as an engineer. I mentioned at the beginning that engineers apply principles of natural science in their work, and I'm often asked by my students about the relationship of engineering and science. Having worked both as a scientist and an engineer, I have my own perspectives on this. Certainly one of the greatest joys for a scientist is to understand something about the universe around us which people never understood before, or to discover something in the universe that people were unaware of. As an example, Hans Bethe was a very famous astrophysicist. Back in the earlier part of the 20th century, one of the key questions in astrophysics was to try to understand the source of energy that powered our sun, which we know now to be nuclear fusion. And it's a very complex process, and people were struggling with this. They couldn't quite figure out how it would work. And I once heard Bethe give a lecture where he described that kind of eureka moment when a key unknown aspect all of a sudden became clear to him. And I heard him once describe the joy that he had for a brief afternoon where he realized that he was the only person on the earth who really knew why the sun shined. So understanding the universe in new ways is a critical part of science, as is discovering things that nobody has seen before. This is an image taken in 2014 by the ALMA telescope down in Chile of a planetary system in the process of formation around a nearby star in our galaxy. I mean, it almost looks like an artist's conception, but this is real. This is something that people have been thinking about for decades, and now we're actually able to see images of these things. But having said that, we have to remember that you can understand why the sun is shining, but the sun has been shining for billions of years. We didn't make it shine. And you can discover planets going around another star, but they've been going around that star long before human beings ever existed on the planet Earth. So we learn things about how the universe works, but the universe has always been there. Whereas engineers try to create things that never existed before. And that's the greatest joy for an engineer, is to create something new, something that people hadn't been able to do before, such as the International Space Station. The Hubble Space Telescope has transformed the science of astronomy, rewriting astronomy textbooks many times over. And yet it wouldn't have been possible without tremendous work on the part of the engineers who designed it. In order to be a successful space scientist, you really have to understand the engineering of satellites so that you know what is possible and what's not possible. And similarly, to be successful as an aerospace engineer, you really have to understand the physical principles, to understand the environment that you're going to work in, to understand the physics, the chemistry, and the physics of materials that you're going to work with in order to design the systems that the scientists are then going to use in order to discover the secrets of the universe. So basically, I look at science and engineering as being interlocked. And a good engineer has to understand science, and a good scientist has to understand engineering. That's the way it's always been, and I think that that's a very important concept for students of aerospace engineering to understand. So let's move from engineering in general to take a closer look at what's involved in aerospace engineering. I often think of aerospace engineering as learning to fly in 3 dimensions, leaving the surface of the Earth, flying through our atmosphere out into space. One of the things that is fascinating about aerospace engineering is it involves a tremendous number of sub-disciplines. Let's take a look at a modern airplane, which illustrates some of the many things that aerospace engineers have to be concerned with. With an airplane, of course, we're flying through the atmosphere, and so we need to understand fluid dynamics. And whether you have an airplane or a rocket, we're leaving the surface of the Earth, and we have to overcome gravity, which means that weight is extremely important. So we have to make our structures very light. And yet they have to be very strong to be able to withstand the tremendous forces that we put on them. So one of the unique things about aerospace engineering is learning how to make systems that are both light and strong. And that's what's involved with what we call structures and materials. And of course, we will have to make things go very fast, so propulsion is an important part of aerospace engineering. And we have to understand the dynamical behavior of the vehicles we design so that we can design control systems which allow us to make them do the things that we want them to do. And of course, whether you're in an airplane or a spacecraft, you need to be able to communicate with the outside world, and so communications systems are important. Software and computers nowadays sometimes make up 50% of the cost of a modern aerospace vehicle. And finally, Our systems have to take account of the limitations on the human body, and we have to be concerned with how humans interact with the increasingly automated environment of modern aerospace vehicles. At MIT, we've developed a concept that we refer to as CDIO, which stands for Conceive, Design, Implement, and Operate. This concept actually applies to all types of engineering, but let's take a look at it as it applies to the Apollo program, which took us to the moon. President Kennedy, back in the early 1960s, said,
"I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth."
That was the basic concept. President Kennedy said, "We will send a man to the moon and bring him back safely before the end of the decade." Then it was the job of the engineers to actually design the systems which would make this possible, which involves a lot of analysis. And once the design is complete, then you actually move into the implementation, which is building the system, testing it, making sure that it's ready to go, and finally the operation, which, of course, as we know, was enormously successful, and President Kennedy's initial concept was finally realized. Let's take a brief look at what the qualities are that someone needs to be an aerospace engineer. And to do this, I'm going to use a document which was published by the Boeing Company on the basis of many, many years of experience in large engineering projects. First of all, to be a successful engineer, you have to understand the basic science and math that you're going to be using throughout your career. And of course, nowadays that includes competency with information technology. We build things as engineers. And when you're working for a company which is going to build large numbers of aerospace systems, then it's very important that when you're designing something that you understand how that object is actually going to be manufactured and used. So understanding the entire process, which we referred to again as CDIO, even if you're only at the beginning of it in designing, you have to be able to imagine how your system is going to operate through the end of its life. And engineering is multidisciplinary. To be successful, even if you're working on the, say, structures and materials part of an aerospace system, you better understand how that relates to the propulsion and the control systems. And basically, a systems perspective is a critical part of aerospace engineering. And then engineers work in a societal context. We have to understand why we're designing the systems that we're going to be building and operating, what need they fulfill in society, and we relate to customers, particularly if you're working in industry. It's great to design something, but if it's something that people don't want, don't need, and aren't going to buy, then it's not going to be a success. I talked about the enormous importance of communication, and Boeing confirmed this, that they want their engineers to be able to communicate with one another, to share ideas. Ethical standards are critical for the safety of the systems that we're building because human lives depend on the work that aerospace engineers do. Some other aspects, creative thinking, being able to critically analyze concepts, the flexibility to adapt as your requirements change. And of course, engineering is not static. Science makes progress, people devise new techniques, and if you're going to be a successful engineer, you have to be able to continually adapt and learn new things throughout your life. So education is an ongoing process. And finally, as an engineer, you will almost never be working just on your own. Individual people don't design an entire rocket or an entire satellite or an entire airplane. You have to be able to work as part of a team. So cooperation and the ability to work as part of a team is critical for success as an engineer. Some of you may be thinking about careers in aerospace engineering. So I thought it would be interesting just to look briefly at some of the different places where aerospace engineers work. Well, the vast majority of aerospace engineers work in large aerospace companies like Lockheed, Boeing, and Airbus. But actually there are now a lot of new entrepreneurial startup companies, particularly in the space business, like SpaceX, Virgin Galactic, and these are attracting a lot of engineering talent. Of course, many aerospace engineers go to work for government, either at established space agencies like NASA, ESA, the European Space Agency, or in other government agencies. In the United States, we have the Federal Aviation Administration, National Transportation Safety Board, Environmental Protection Agency, Department of Energy, or, of course, the military in many countries has a need for talented aerospace engineers. Then there's the possibility of working in research at either private or government laboratories. In this country, the United States, we have the Draper Laboratory near MIT, the Applied Physics Lab, the National Institute of Standards and Technology, and so on. Or working in academia. Many engineers are working at universities. And then there are some non-traditional disciplines. As an aerospace engineer, you are going to get a basic background in all aspects of engineering, which will allow you to work in other types of engineering if you so desire. Or sometimes even in non-engineering areas, because as an engineer you've learned about analysis, problem solving, the use of computers, and these are valuable skills for Wall Street analysts, for doctors, law, and the consulting business. So there's a wide variety of possible careers for someone with a good background in aerospace engineering. In our department at MIT, we conducted a survey recently of some of our graduates to find out where they were working. This is a chart where the places where they end up are sized according to the number of people who went in. So you can see far and away the largest number of our alumni are working in aerospace and defense, and quite a few are working in education or in the computer business. And the important thing to realize is that there are many non-traditional aerospace opportunities which are available and which many of our alumni have taken advantage of. And finally, we asked our alumni not only where they were working, but what they're actually doing. And so you can see many different things, from system designing to running tests, supporting business opportunities. So those of you who are thinking about aerospace careers should be aware of there's many opportunities which will be open to you. So now that we've had a brief look at the nature of engineering and a little more closely into the nature of aerospace engineering, I'd like to take you on a brief journey into the third dimension as we leave the surface of the Earth and travel outwards into the universe to enjoy what I refer to as the aerospace perspective.